Hey, welcome to The Explainer, where we break down big ideas. Today, we are jumping right into momentum. It's the hidden science behind pretty much every collision and explosion you can think of, from billiard balls clacking on a table to, stars going supernova.
Okay, let's start with a question that sounds a little bit like a riddle. What could a massive charging elephant and a tiny speeding bullet possibly have in common? Well, in the world of physics, they actually share this incredibly powerful, invisible quality. And that quality is called momentum. The easiest way to think about it is just oomph, More scientifically, it's the quantity of motion an object has. And it's not just about how fast something is going. It's this crucial mix of how much stuff is moving and how fast that stuff is moving.
Now, the official scientific definition is actually really straightforward. Momentum is simply a moving object's mass multiplied by its velocity. That's it. And it's this simple relationship between those two things, mass and velocity, that makes momentum so fundamental to, everything.
The formula itself is just beautiful, isn't it? P stands for momentum, and it equals m for mass times v for velocity. This little equation tells you something really important. A huge object moving kind of slowly can have the exact same amount of oomph as a tiny little object moving incredibly fast. It's all about that trade-off.
So let's look at the units here for a second. We measure mass in kilograms and velocity in meters per second. So what's the unit for momentum? Well, it's just kilogram meters per second. It literally describes what it is, a certain amount of mass moving at a certain speed. No fancy names, just what you see is what you get.
Okay, let's put some real numbers on this. Imagine an ice skater, right? They have a mass of 60 kilograms and they're gliding along at a pretty quick 15 meters per second. You multiply those together and you get a momentum of 900 kilogram meters per second. That's a real solid number we can work with.
So now we know what momentum is, but what if we want to change it? See, an object's momentum isn't set in stone. If you want to get something moving, or maybe more importantly, bring it to a stop, you have to apply a force for a certain amount of time.
All right, this equation looks a little more involved, but trust me, it's incredibly powerful. It tells us that force, F, equals the change in momentum divided by time. And that change is just the final momentum, that's mv, minus the initial momentum, mu, all divided by the time it took for that change to happen.
What this is really telling us is that the force you feel is all about how fast the momentum changes. If you want to make a big change in momentum, like right now, you're going to need a huge force. But if you can stretch out that change over a longer period, the force can be much, much smaller.
And here is where this all clicks into place in the real world. This very principle is one of the most important applications of physics out there. Car safety. I mean, this isn't just theory. This stuff is actively used to engineer cars that literally save thousands of lives. So, have you ever really thought about how things like crumple zones and airbags actually work? It's not just about having some extra padding around you. They are actually really sophisticated systems designed specifically to manage momentum.
The whole secret is right back here in our force equation. Now, think about a car crash. Your change in momentum, the delta P, is fixed, right? You're going from, say, 60 miles an hour to a dead stop. Engineers can't change that. So what can they play with? The other two variables, force and time.
By designing the front of the car to crumple, to literally collapse, engineers are cleverly increasing the time it takes for you and the car to come to a halt. And if you look at the formula, if you make t, the time on the bottom, bigger, then the force F on the top has to get smaller. A longer crash is a gentler crash. And that is the physics that keeps you safe.
Okay, this brings us to one of the most profound, most beautiful ideas in all of physics. While you can change the momentum of one single object by pushing on it, the total momentum of a whole system of things interacting with each other, well, that can never be created or destroyed.
This is the principle of conservation of momentum. It's a golden rule of the universe. In any interaction, whether it's two things colliding or one thing exploding, the total amount of momentum you start with is the exact same amount you finish with. It just gets moved around, redistributed among the parts.
Now, for this law to be perfectly true, we need what physicists call a closed system. That's kind of like a perfect little bubble where no outside forces like friction or air resistance are messing with the results. Now, of course, the real world isn't a perfect closed system,
but this principle is still an incredibly powerful way to understand what's going on.
So where do we see this in action? Well, it's demonstrated perfectly in two classic physics scenarios: collisions, where things smash together, and explosions, where things fly apart.
Let's just look at a simple collision. Before it happens, we've got one trolley moving along with 6 units of momentum. The other one is just sitting there, so its momentum is 0. The total for the whole system? 6. After they hit and stick together, the combined mass is way bigger, so to keep that total momentum at 6, their new combined speed has to be much slower. See? The momentum wasn't lost, it was just shared.
Now, explosions work with the same rule, just in reverse. Before you fire a cannon, everything is perfectly still. Total momentum is 0. But when it fires, the cannonball shoots forward, gaining a huge positive momentum. So, to keep the total at 0, the universe demands that the cannon itself must recoil backward with an equal and opposite negative momentum. They cancel each other out perfectly.
And the reason that works is because momentum is what we call a vector. That's just a fancy word meaning it doesn't just have a size, it has a direction too. And that direction is absolutely crucial. We can just decide to call forward motion positive and backward motion negative. So when you add the cannonball's positive momentum to the cannon's negative recoil, you get 0. The law holds up.
So, after all these formulas and collisions and cannons, what's the big picture here? What's the main thing you should really take away from all this?
Momentum isn't just some formula you have to memorize. It is a core fundamental property of our universe. It's this conserved quantity that governs how everything interacts, from tiny particles smashing together in an accelerator to entire galaxies colliding. It ensures that the cosmic books of motion always balance.
And that leaves us with one last, really big question to chew on. If the whole universe is a closed system, and its total momentum can't ever change, then where did the very first push come from? It's a thought that takes this simple idea about motion and connects it to the deepest mysteries of the cosmos.